Okay, hello physicists. Welcome to our March 5th edition of physics. Um, Today we're basically done with our information for the Unit 2. A week from today we're going to take a test for this unit. So next week we'll have some time to review, as no doubt you might have forgotten stuff that we did at the beginning. But today, my goal is just to sort of go over a bunch of problems related to power and energy and try to coalesce this stuff. Now, the good thing about this is that it means I'm not going to be dumping a lot of new information on you on this video, but I am hoping to go through enough questions that you start to see the patterns. I should also say there's a quiz today, so if you have only time to do one thing in this course today and you're watching this video, I would recommend going and doing the quiz. All right, so what did we discuss on Wednesday? Well, we discussed how we could start to do problems by just writing down the energy, and if we have a closed system where energy is just exchanged between parts of that system and not made or destroyed. If we consider the whole universe as a system, that would always be true. That's our claim is that the total energy of the universe, for instance, is always conserved. But we always are picking a little subsystem where energy is approximately conserved within that subsystem of just a couple objects. And what we've been doing with problems in this chapter is you say, okay, add up all the kinds of energy that we have before, at the beginning of our problem, when we set it up. And we have different types of energy. We have the energy of motion, the kinetic energy that has to do with the mass and the speed of the translation. And then we have other types of energy that have to do with the position of the object. So gravitational potential has to do with going from lower to higher. Elastic potential has to go from a spring being unstretched to being stretched. And what we do in this type of problem is we just add up all the types of energy equals add up all the kinds of energy at the end. And if there's no energy going in or out of our system, that makes it real easy to try to keep track of our variables throughout. And of course, we do need to, since in a real system, if you're not considering the whole universe as your system, you're going to have energy sometimes going out of your system or coming in. We dealt with that in sort of a little bit of a schematic way. Now, I should also just say, I talked to someone on Wednesday who told me that she thought I was making it sound as though I didn't believe in energy. And maybe I don't. But upon further reflection, after she told me this, I said I should probably clarify. I do believe in energy. I believe in energy in the same way that I believe in things like the rule of law or the meaning of the word horse or human rights or anything else like that, in that these are all very useful ideas that humans use to try to get a handle on the situation that they're in, which is this very mysterious thing. And so we as physicists are, in my view, doing the same thing that people in any discipline throughout the university are doing. We're inventing tools to help us to get a handle on what's going on. Okay, so here's a situation. As always, I'm doing some of these questions with a framing that I want you to think about the quiz that's up today. Here's a nice example. This graph shows the potential energy as a function of distance for an object moving along the x-axis. At which of the labeled points does the object have the greatest speed? Okay, so this is potential energy. This is effectively, you can really literally think of this as like the shape of a roller coaster. You have a you have an object, or you have a roller coaster car up here, and as it goes down the slope, it starts to lose potential energy, but it gains kinetic energy. Now it's losing kinetic energy, gaining gravitational potential energy. Now it's losing gravitational potential energy, gaining kinetic energy, and then it slows down. Finally here it's at some constant gravitational potential, so its kinetic energy is a constant along this stretch, as is its so its kinetic energy and its potential energy are constant along that stretch. Okay, so it asks, at which of the labeled points does the object have the greatest speed? Well, it's got to be right there. How do I know? Because the total amount of energy is constant. The total amount of energy in this problem is the kinetic energy plus the potential energy. So at the kinetic energy plus the potential energy initial equals the kinetic energy plus the potential energy final. Okay, initial, final, final. So in this case, one way I could set up this type of problem would just be mgh. Consider that the kinetic energy, for instance, might be 0 right there if I just barely tap the car. And then it speeds up, speeds up, speeds up, speeds up, speeds up. Here, if I consider my height as 0, my potential energy as 0, I would have all of that energy transferred into my kinetic energy. And then at that point, I would have my greatest speed because I have my greatest kinetic energy. And there my potential energy could be written as 0. And remember, all we're ever really measuring is differences in energy. We don't really have to care about absolute values for energies. In higher level physics, physicists sometimes get confused about these issues because in general relativity, the gravitational bending of space-time or whatever depends on the energy density in the space, and so in that circumstance, it does seem like there needs to be some thought about the absolute energy density rather than just differences. But in basically every problem that you come up with in physics, it's always just differences in energy, not absolute energies. Okay, here's another just sort of a silly problem that I made up last night to try to drive this home again. Remember, in our problems for this that are very simple problems, we only have to worry about 3 types of energy. Kinetic energy, 1/2 mv squared. So that just depends on the speed and the mass of the object. We have gravitational potential energy, which in this case is going to be m times g times h. So if you define a height at 0, h would be how high you lift your object up a hill, or put it on a table or something like that, and then you can get that energy back by dropping the ball off the table. And then your final type of energy that we care about in this course is going to be that elastic energy, 1/2 kx squared, where this x is how much a spring has been stretched. So you can store energy in a spring by either squishing it or by stretching it, and you can get that energy back out by letting it go, and it can push a ball or stop an object that's coming in to squish it or whatever. Okay, so here's my silly example. Let's suppose that you have a skier going down a hill, and that hill has some height of 5 meters. And notice I didn't have to even say anything about what angle that is. I just need to put this skier as a mass of 60 kilograms. And she's going to slide down the hill on her skis. We ignore friction for the time being. And then down here, she has some speed. And I ask, how fast will she be going on this flat slope at the bottom? Okay, well, this is sort of a baby question, but I'm willing to do it. What kind of energy does she have at the top? She has gravitational potential energy. What kind of energy does she have at the bottom? If we have this height at 0, this height at 5 meters, we can say that the gravitational potential energy there is 0, and all of her energy that we need to care about is the kinetic energy. So I could just set up this problem, mgh equals 1/2 mv squared. And I could realize that the masses cancel out in that particular case, and it would be easy to find my v as just square root of 2gh, or in this case 2 times 9.8 meters per second squared times 5 meters. Okay, so I can plug that in my calculator, and I'm going to get the speed in meters per second. Okay, then the second part of the question. As the skier continues upon the flat slope, she notices, oh no, a springy ski trap. A cloth sheet that stretches like a spring to stop skiers from going forward. Is that a real thing? No, I made it up. Okay, if the ski trap stretches 3 meters while stopping her, what is the trap's spring constant? Okay, so I'm going to just not even pretend here. I'm going to draw this like a spring, and it is going to be stretched by some amount of 3 meters. And how would I do this problem? Well, at the end of the story, she is not moving. She doesn't have any gravitational potential energy anymore. So all of that kinetic energy has been transferred into elastic potential energy. So I could just say kinetic energy right here is equal to the 1/2 k x squared. And I've been told that that x is 3 meters. I really should be writing it as a delta x, but I'm being a little sloppy. Okay, but look, we realize also that the kinetic energy here was just related to the gravitational energy there. So I can also just write mgh equals 1/2 k x squared. The question asks, what is the trap's spring constant? Remember, the spring constant is this number in here that tells you how many newtons per meter you get. So K is a number in newtons per meter, and it tells you how much force you get for how much distance you stretch the spring. So if you stretch it a meter, you should get K newtons back. If you stretch it 2 meters, you should get 2K newtons back. Okay, so looking at this problem here, I can go ahead and easily solve this. 2mgh, multiplying both sides by 2, divided by x squared equals k. And so yeah, in this case, my k is going to equal 2 times 60 kilograms times 9.8 newtons. Oops, let me give myself a little more space. There I go. Luxurious space. 2 times 60 kilograms times 9.8 newtons per kilogram times 5 meters over 3 meters squared. All right, so let's see, am I going to get the right units? This cancels out the kilograms. A newton meter is a joule, but then I divide it by meters squared, so that gives me back newtons, and then I divide it by another meter, and that's going to give me newtons per meter. So that'll give me my correct answer, and I can stick in numbers then. Okay, so that's the idea. You're going from one type of energy to another type of energy. Now let's take a look just quickly at another practice problem with non-conservative forces. Okay, so this is another problem from your book, but the idea is that if you have something like friction, that can act as a negative source of energy. How is it a negative source of energy? Is that a contradiction? No, it just means that energy is leaving your system and it's going into thermal energy of the floor. It's being leaked out. So let's just look at an example of this. A collie drags its box across the floor, applying a force of 8 newtons. Okay, so my force of collie equals 8 newtons. The kinetic frictional force acting on the box has a magnitude of 5 newtons. Okay, so the collie's pulling forward, the frictional force is pushing backwards with 5 newtons. As the box is dragged through 0.7 meters along the way, okay, so we're going to go 0.7 meters, 0.7 meters along the way. What are the work done by the collie's applied force and the increase in thermal energy of the bed and floor? Okay, remember, work, the amount of work done, tells me how much the energy is changing on this object. So in this case, we're sort of backing away from the energy paradigm back to our forces thoughts, and we're thinking about basically the speed of this object. More force is being put in one way than on the other way. This object is doing positive force because it's pushing in the direction that the box is going. The force of friction is doing negative force because it's pushing opposite the direction, the force of friction is doing negative work, positive work from the collie, negative work from the force of friction. The negative work is causing the thermal energy of the bed and floor to increase. So the energy is going out of the box, it's going into the floor, heating up a little bit. So what is the work of the collie? It's going to be just the force times the displacement times the cosine of the angle, which is 0. So it's just going to be 8 newtons times 0.7 meters. Okay, and if I'm thinking correctly, I think that should be 5.6 joules. Okay, then the work done by friction, the work of fric, is going to be negative. Why? Because I have the direction of the object, or the displacement of the object, and the direction of the force are opposite. So the cosine of 180 is -1. Also, they're pointing opposite direction. It's slowing it down. It's taking away possible speed. So there's your -5 newtons times 0.7 meters. And that would be, let me think, 5 times 7 is 35, so I think that would be 3.5 joules minus. Okay, so if you wanted to think about the net work done, it would be the work done by the collie plus the work done by the friction, and these have opposite signs, and then your kinetic energy of the box initially, your kinetic energy of the box at the final stage equals the kinetic energy of the box at the initial stage plus that net work. So in other words, you could find the net force. So the net force would be 8 newtons minus 5 newtons is 3 newtons. So if you took 3 newtons times 0.7 meters, you'd get 2.1 joules, and that's the same thing that you would get by splitting it up. Okay, so two ways to think about the same thing. All right, so as I said, we're just doing a bunch of problems today. Here's an example that I think is a good one to think about. If you look at the picture of the guy, this is an experiment I used to do when I was a high school teacher. In fact, the thing that's easy to forget when you're in college is that you just have a lot of time to kill when you're in high school, because you're there every day. You've got to figure out something to do for an hour every day. And so you'll remember that we've talked about the centripetal force as being m times v squared over r. So this is your F equals ma. And one little cute experiment that you can do with this is, let's say you get a little rubber straw, and you've got some tension force here that's holding the ball up as you spin it around. And you have the force of gravity that essentially is providing that tension force in equilibrium. So there's tension pulling up on this, there's the force of gravity. And what this does is that what you're effectively doing is you spin this thing around, and it has some R, and you can go ahead and so you put some masses down there. Then you start spinning this thing around, and you try to figure out what radius that object is going to reach equilibrium at. And that can be measured, and your V in that case would be 2 pi r over the amount of time. So you're using little stopwatches measuring the amount of time, trying to estimate the radius, and then that way allows you to directly measure the sort of the centripetal force, and noticing that m times v squared over r actually works, because this object also has some mass. Okay, it's a cute little example. All right, now let's see. A 5 kilogram ball on the end of a chain is whirled by a constant speed of 1 meter per second. So in this case, that's 1.0 meters per second in a horizontal circle of a radius of 3.0 meters. What is the work done by the centripetal force during 1 revolution? Let's think about it. What is our equation for the work is going to be the force times the displacement times the cosine of the angle between them. So what is the angle between the force and the displacement in this type of a problem? So I'm pausing because I want you to try to think about this. If you want, you can always pause these videos and see if you can figure out the answer for yourself. 0 joules. How do I know that the amount of work done is 0? Well, it's because in this case, I'm looking at this from the top now, the force is always towards the center, and the displacement is always going tangent to the circle. So the angle here is always it's always perpendicular. So the work, which is the force times the displacement times the cosine of the angle here is 90 degrees, and cosine of 90 degrees is 0. So that's one way to see it. Another way to see it is that what's happening here, work is the amount of energy that's put in to change the speed of the object. If your object is just going around at a constant speed, it's not changing its kinetic energy. It has the same amount of kinetic energy at the beginning of the story as the end of the story. Okay, so in that case, no change in no change in speed means no work has been done. No net work, I should say. As we saw in the last problem, sometimes you can have positive work and negative work. So take that with a grain of salt. But in this case, the force being applied is just acting to change the direction. It is not acting to speed the particle up or slow it down. So there's zero work done. I should say there's a similar fact that if you just hold a heavy block like this for a long time, you feel tired, but technically there's not any work being done in the way that we're using that word in physics class, because it's just a force. It's not acting over some displacement. Okay, sort of tricky. All right. Now today I'm going to only add in a couple new ideas. Here's one of the new ideas I want to hit you with. When we derived our expressions for potential energy, we did it by starting out with a force and integrating it over a displacement. And we realized that work was going out of the particle, but it could be gotten back. And that's essentially the process. So for instance, in our gravitational force, if we had the amount of potential energy going from height equals 0 to height, or from x equals 0, or y equals 0 to y equals h, the force of gravity in that case is just minus mg in the y direction. And then if I wanted to find the change in gravitational potential, you'd say that was minus, as I'm going from 0 to h, integral from 0 to h of minus mg times dy. And this is a definite integral, and you can find it, and it would just be mgh. Okay, so that's where we got that out. Now, on the other hand, we can go ahead, or for the purposes of this, let's say that I'm integrating from 0 to y, so I would get mgy. All right, now let's say that you wanted to get back out what your force is. Well, the sort of the opposite of a integral is a derivative. So if you wanted to go from this idea of potential energy back to a force, how would you do it? Well, if you took an integral to get the energy, you would have to take a derivative to get the force. Okay, so my force in the y direction then would be minus du dy in this case. So it'd be minus d dy of mgy. So my gravitational force in this case, I could get this back as minus mg. Okay, so notice all I've done here, I've just gone in a circle. I went integrated, and then I went back down. However, this is sort of a useful tool because often what physicists will do is they'll take a bunch of particles, they all have a different potential energy contribution, add it up, and then you put in a new particle and figure out what sort of forces are on it, not by calculating all of the vector sum of the forces. You just find how the potential energy is changing in space, and you go directly to the force. So, for instance, here's a nice drawing where, again, we have our drawing of a roller coaster. Keep in mind that if this were a roller coaster, its height would have to be divided by 9.8 to give you to make this a height on that axis. But that's sort of a detail. So here you have the potential energy versus x. How does this translate to the amount of force that's causing this to go forward? Well, as you know, as you're going downhill, you get a big force pushing you forward. As you're going uphill, you have a force that's pushing you backwards, essentially slowing you down as you go uphill. Then you go downhill, you have another force pushing you forwards. Then as you get to this flat spot, you don't have any change in potential energy anymore. There's no force, and therefore the force goes to zero. The potential energy is thought of as a constant. Okay, so let's just do a quick example with this. Okay, the graph shows the potential energy as a function of distance. Okay, this is just working again with the problem that we saw earlier. For an object moving along the x-axis, at which of the labeled points does the force acting on the object have the largest magnitude? Okay, so force is the change in the potential over the change in x. This is the potential. What does this look like? Well, to me it looks like a slope. So where is our slope the biggest here? It's got to be right there. Okay, so wherever your slope is the biggest, that's where you have the biggest force. And that sort of, you know, that tracks with your experience if you've ever been on a roller coaster. Now notice this slope is negative. The minus sign here keeps track of that so that the force is in the plus direction. It's pushing you in this direction. Along this way, you'd be slowing down, so the force that you'd track would be along that direction. Okay, so sort of interesting. Let's try it again. The graph shows a potential energy as a function of distance. At which of the labeled points does the force acting on the object have the least magnitude? Where would it have the least magnitude? Well, as we said, this looks like a slope. What's our slope right at A? If this is flat, the slope is 0. So if your slope is 0, your force instantaneously right there would be 0. How about right here? Again, it's at the bottom of a valley. The slope is 0, so the force is 0. Bottom of a valley, slope is 0, force is 0. Here again, our potential energy is not changing. So if it's flat, the slope is 0, so the force is 0. So we have to conclude that the force is the same at each of those 4 points. All right, a little interesting. Okay, so here's our last one for today of these quiz questions. Let's say that you have an object that's initially at height y1. After a time interval t, the object is located at a height y2. Okay, so here's y1. Let's say that our object is dropping. That doesn't matter. We can think of it either way. And it takes some time. This is at y1 at time, and there's a time interval t between these two heights. It asks, the work done by the gravitational force on the object is dependent on which of the following quantities? Is it the difference between these two heights? Is it the path taken between there? So you could take lots of different paths. You can go back and forth. The time interval taken from y1 to y2, choices A and B, choices A and C. What are we going to say? So this problem has to do with what we mean by conservative forces. If we're talking about a conservative force, all we care about is the starting position and the final position. And so the whole thing about how much gravitational energy has been released is going to just depend on the change in y. It doesn't matter what path you take. It doesn't matter how much time this took. If we want to talk about the work that has been done by the gravitational force, that force is acting in this direction, and it only is going to depend on how much your distance in that particular direction has changed. Okay, so that's sort of what we mean by a conservative force. Okay, I just want to touch briefly on power again. Yesterday we talked about how power is the amount of energy that is leaving a system or coming into it per unit time. And we also established that because power is the work over the time, this is the force times distance over the time, and because distance over time looks like a velocity, this is effectively your force dotted with this, the velocity. So force times the speed times the cosine of the angle between them. Now, one thing I do want to sort of drive home is that, at the beginning of this this lecture, I spent a little bit of time, trying to sow doubt in your mind about whether energy was real. But that is sort of just a philosophical speculation. I don't want you to think that it has any real bearing on energy policy, or whether or not you think the Green New Deal is a good thing or a bad thing or anything like that. The fact is that we use this language of energy all the time, and it's relevant over enormous scales of different phenomena. So, for instance, a supernova is an exploding star at the end of its lifetime, and the power in watts of that is about 10 to the 37th. Okay, that's an enormous. That's joules per second. So that's not just the total amount of energy. It's exploding, and it's enormously bright. There are records from the ancients of seeing these things show up in the sky. Some people think that, for instance, the Star of Bethlehem in the Bible might have been this sort of thing, where this supernova shows up, and they see it in the sky. It's an unusual thing. Who knows? Now, look at the size of that compared to, for instance, the size of the power output of our sun. Okay, we're talking 10 to the 26th joules per second. Now, if you're looking at this 10 to the 26th times to 10 to the 27th, we're talking about 10 to the 11th orders of magnitude difference. So that means that this supernova looks like 10 to the 11th. That's about 100 billion times brighter than our sun. Now, notice the Milky Way galaxy is also about 100 billion times brighter than our sun. And that's an interesting fun fact, because how can it be that the Milky Way, that's just our local galaxy, there are galaxies far off as well, how is it that it has about 100 billion times greater power than our little sun? Well, roughly the reason is because there's about 100 billion stars in the galaxy. Makes you think. Now, let's say that I look at the difference between, for instance, the sun and a bolt of lightning. A bolt of lightning is releasing a tremendous amount of power. You've seen it in the sky. It goes, pew, and there's a big amount of light that's let out in a short amount of time. So that's a big amount of power. This is about 10 to the 12th joules per second. How different is that from the sun, though? Well, 12 to 26, that's about 10 to the 14. So that's about 100 trillion times different between the sun every second and a lightning bolt in the 1 second that it goes. Okay, well, what about a strong football player? A strong football player is going about 10 to the third joules per second if they're really going at full tilt and running into someone. Notice this is about 10 to the ninth. This is another billion. But notice we're going up by like billion, trillions, 100 billion. And so the vast difference between the amount of power being used by a football player and a supernova, it's hard to imagine. But you can keep going down this scale. You can keep going down the scale from a football player to, for instance, a pocket calculator. That's about, football player is 10 to the third. Pocket calculator is 10 to the minus third watts. Between these two, there's a 10 to the sixth difference again. So that's 1,000,000 times more energy is being used per unit of time by a football player than by a pocket calculator. I mean, if you imagine it, any reasonable football player is not going to be able to be powered by those little batteries in the back of your calculator for very long. So, even if I've been, sowing a little bit of doubt about the efficacy of this, it is the sort of language that gives us the ability to talk about phenomena that are vastly separated in orders of magnitude, and so that should give us some interest. Now, another point that I just want to mention for those of you who are interested in this sort of thing, if you go on in physics, and take a junior level course in physics called analytical mechanics, there's an interesting form of this that has to do with the calculus of variations and what you do to solve problems where you have lots of particles and you want to find out how all of them are moving. Essentially, what you do is you write down something called a Lagrangian. And this is just the sum of all the kinetic energies of the particles minus the potential energies of all the particles. And by doing that, nature essentially tries to minimize the Lagrangian, or minimize changes in the Lagrangian. And by doing this, you can use the calculus of variations, branch of mathematics, to try to see how this can be minimized in time. And you can jump directly from that statement to finding the forces for each one of those particles. So this language change from forces to energy is very powerful. This stuff was all developed in, I guess, the 18th century, in the century after Newton was alive. And there's a lot there. We're not going to do it in this course, but just know that if you decided to go into this sort of thing, become a professional, like yours truly, there's a long road where there's a lot of investigation that's been done into this type of thing. Okay, so what did we learn today? Potential energies can be found by taking the integral of force, and you can undo that by taking the derivative, so you can get forces back out from potential energies. 2, methods involving energy sometimes allow for dramatic shortcuts. And we've been doing some of those shortcuts by just writing down the energies, solving the problems. But know that that's not the end of the story. There's this whole field called Lagrangian dynamics. Beyond that, there's something called Hamiltonian dynamics, and it's a pretty deep subject that you can spend a lot of time working on. And even if I'm a little bit of a doubter as to the realness of a lot of things, this type of language allows us to discuss vastly different orders of magnitude of power output. So even if I have some philosophical quibbles, this is very useful stuff for wrapping our arms around a wide range of physical phenomena. Okay, so reminder, quiz today, homework due on Monday. So please, if you have questions, email me, set up a Zoom meeting. I will be happy to work on this stuff with you. And thanks for watching.